Awesome. Thank you all very much. So this is getting the best performance with PySpark. Hopefully you care about PySpark. If you don't care about PySpark, some of the stuff will apply even in regular Spark too. So I'm Holden. My preferred pronouns are she or her. In case you forget, it's tattooed on my wrist. So try not to fuck it up. I'm also wearing a Spark dress, which I think is pretty rad. This is some code from the Spark context. Sadly, it's Scala code, and I'm giving a Python talk, so it's not like 100% on, but I think it's pretty close. Anyways, I'm a software engineer at IBM's Spark Technology Center here in San Francisco. Previously, I was at Alpine, Databricks, Google, Foursquare, and Amazon, and I've sort of been working not always on Spark, but sort of in this big data and search and recommendation space for a while. I'm also a co-author of Learning Spark, another Spark book, and yet another Spark book I'm a co-author of is in early release, and I'll try and convince you all to buy that one soon, because I get money if you do that, so that's cool. If you want to follow me on Twitter for sort of just random pictures of my cute stuffed animals, this one's name is Boo. You can follow me on Twitter, it's just Holden Caro. The slides from today's talk and most of my other talks are up on SlideShare, so it's just this SlideShare address right here if you want to take a picture of that so you can find my slides. And I've got a bunch of code on GitHub, and I have all of my Spark videos. I try and make a YouTube playlist. If you're interested in sort of just learning about some random Spark stuff, you can go and watch some of that stuff. So I'm going to talk about sort of who I think you all are. Going to do a really super quick background on how PySpark works, sort of compared to just regular Scala Spark. Then we'll talk about some just general techniques for RDD reuse. We'll talk about sort of considerations for key value data. We'll talk about how Spark SQL can be amazing. At this point in the conference, though, I'm pretty sure everyone's sold on Spark SQL being amazing. So this may be some preaching to the choir. Then we'll talk about how to call Scala code from Python. And I know this is a bit crazy to do in a Python talk, but sometimes for performance, we actually really do want to do our stuff in the JVM. And then I'm going to talk about some really sketchy plans I have to make PySpark go fast in the future, or as I like to think of it, Python vroom vroom. Very serious business. So yeah. So the short version is we can go from this sad cat to this very happy unicorn. The very sad to happy Sparkland. So today we're going to be focused on the core Apache Spark and SQL DataFrames, and we're not really going to dive into streaming or even structured streaming. If you're super interested in R, this stuff probably isn't super useful to you. But if you're a Scala person, I still think this stuff has some relevance. I'm hoping you're all nice people. You've laughed at many of my corny jokes, so I'm thinking that's a yes. If you object to pictures of cats, you're going to have to ignore the top right-hand part of pretty much all of my slides. And I'm hoping everyone knows some Apache Spark, but the one which I wasn't sure on is how many people currently use PySpark? Yay! Okay, that's great. I'm super excited. Okay, cool. And you all want to scale your Spark jobs, obviously, and make them go super fast. Cool, that's great, awesome. I'm super happy. So we're going to take a quick detour into the mysterious land of PySpark and how it works. So how does PySpark work, right? Spark is written in Scala. At the end of the day, PySpark works with a solid mixture of Py4j, pickling, and a healthy dose of magic. Unfortunately, it turns out that both pickling and magic suffer from some performance problems. RDDs, even just general RDDs in PySpark, are RDDs of pickled objects. And this can be kind of slow because Spark is shuffling around these like giant strings, and it doesn't really know what it's doing. And Spark SQL and DataFrames and datasets, although datasets don't really have the same conceptual meaning in PySpark, avoid some of these problems, and we'll look at that. So what does the architecture diagram look like? This is a really terrible architecture diagram, and you can tell that I clearly should have someone else work with me on my slides. But we can see here on the driver side, we've got our Python process, and it's talking to the JVM, and so it's talking to the Scala driver process. And out on our workers, what happens actually is the Java workers have to shell out to the Python worker. Now it's able to reuse the Python worker, right? These workers are kept around and they don't have to be restarted all the time, but it still has to copy all of the data from the JVM to the Python interpreter, and that's really slow because it actually has to be deserialized in Python there. So how does this impact PySpark? Data has to be serialized more times than it does in regular Spark. And it turns out serialization cost is actually a pretty big component of sort of Spark performance. Multiple iterator to iterator transformation. So if you do a map and then another map and a filter or something like that, it's okay. That'll all get pipelined together inside of a single stage. And you won't have to round trip through the JVM for each operation. But for each like shuffle type operation, you'll end up round tripping through the JVM. Python worker startup takes some time, so your first job is going to run a bit slower than a regular Scala job. And one thing for people who are deploying in Yarn or in memory-constrained environments is the memory isn't controlled by the JVM, and you might actually end up running into a case where your Python interpreter allocates too much memory, and Yarn comes along and goes, whoa, whoa, no. You only have 4 gigs of memory. Good day. And it kills your executor for you, right? And this is because the memory isn't really controlled in the same way that it's done with the Java workers. And the part which most frequently causes me to tear my hair out is the error messages make approximately 0 sense. Best case scenario, you get a Python exception wrapping a Java stack trace, and that's like on a good day. And when that's your good scenario, you know the bad scenario is going to be pretty bad. So, I mean, this architecture, it's really functional and it works, right? Obviously, we're all using PySpark, but there's some serious drawbacks, mostly performance. So hopefully I've convinced you that it's worth hanging around for the rest of the talk, and you're going to wake up, unlike this cat who is taking a nap because they forgot to drink their coffee. And let's go and look at some really simple old standbys, right? This would not be a big data talk if I didn't have word count. And in this case, I'm actually going to have a bad version of word count. And if you spot the part of word count which is bad, don't like shout it out and ruin it for everyone. But so we've got a really bad word count, and then we go ahead and we find out all of the warnings in our same input. And just like this cat that has done something somewhat unexpected, we've done something pretty bad, and it's going to explode for us later. Probably it's going to take a bit longer than the water falling on the cat's head, but it's still going to explode. So the first problem here is we were using the same RDD twice, right? And that's not necessarily a bad thing, right? Like that's great. You know, we can reuse RDDs. But if we don't explicitly tell Spark that we're planning to reuse the RDD, and there's an exception we'll talk about later, it's going to actually have to recompute that entire RDD for us when we perform our second action. In Python, you know, just like in Scala, we can cache them. It doesn't make sense to talk about caching in serialized versus non-serialized in Python because it's always serialized pickled objects. So we can just, you know, persist to memory or memory and disk. How many people run on a shared cluster? Cool. And those of you, do you have preemption enabled? Do your jobs get preempted? Okay, that's less of you. But for those of you with preemption, you may have experienced the joy of having half of your workers die. And that's always a lot of fun. And frequently, like Spark, you know, it continues to work in this environment, right? It just slows down a lot. And part of this is if we've just like cached some data, when we lose that many workers, we actually end up having to recompute a lot of things. So we can checkpoint if we want. And checkpointing is kind of like the really big hammer approach to dealing with this problem. It's very expensive. What it does is it takes our RDD and it writes it out to sort of stable storage. So it's going to write it out to HDFS or CFS or whatever system you're using. And it's going to also throw away the lineage information. This is actually what checkpointing is normally suggested to be used for, and that's when your RDD lineage graph gets really long. But if you're in a noisy cluster where you frequently lose a lot of executors, and you have some really expensive work, it can actually be worth checkpointing. And if you're going to checkpoint, always definitely call persist first, because if you just call checkpoint and then proceed onwards, it'll write all the data out to persistent storage, and then read all the data back into from persistent storage, even if you didn't lose any executors. So definitely like cache it first so that you don't have to always read it back in. You'll only read it back in if you lost some executors. So the other problem with our word count example is we could have key skew. Now, admittedly, since we're doing word count, we probably don't have too much key skew. But maybe if we were counting sales by zip code, we might have more extreme key skew. And group by key is going to explode on us when we have any meaningful amount of key skew. It won't explode on word count, which is, I think, part of the problem and why some people sometimes end up thinking group by key is safe, is because it sometimes is. It's just frequently not very safe. And even if our job succeeds and we have a substantial amount of key skew, we can end up with stragglers. And that's unpleasant, right? Like our job takes much longer than it could if we had a really nice distribution of keys, and that's just sad. So how evil is group by key? It's about as evil as this cat. So pretty evil. And it groups all of the records with the same key together into a single record. And that's just sad. It's completely unnecessary because most of the time when we call group by key, we actually do it because we want to perform some type of aggregate on that key, right? We want to compute the mean, or we want to see like what the distribution looks like in some other way. And there's better ways to do it. Now, if we're in Spark SQL land, everything is great. What happens when we call groupBy in Spark SQL is it actually just returns this group data structure to us, and then we perform our aggregate on the group data structure, and it's able to pipeline stuff for us. But when we're working in the RDD API, we don't have this happiness. Yeah, so if we're in SQL, everything is awesome. So what does it look like besides cats having water dumped on their head? It looks like this record, right? This is, I like to think, handlebar mustaches by zip code. And for people not local to San Francisco, 94110 is one of the mission zip codes. So it has too many handlebar mustaches to fit in a single partition. And if you were doing maybe sales of mustache wax, you would run into a similar problem. Sorry, I find mustaches hilarious. But how would we actually do a proper word count, right? So if we look back to the standard example that we always see, what actually happens instead of group by key is a reduce by key. And with reduce by key, Spark is actually able to look at it and go, oh, hey, this is actually the reduction you want me to perform. And instead of making this giant record and then trying to perform the reduction, it performs the reduction as it's going. And so here we can, you probably can't read this. But if you trust me, and hopefully you do because you're in this talk, you can trust me when I say this, doing it with group by key, took longer, and it involved a shuffle read of 48 kilobytes, working with very big data. Yes, but no, I did this demo on my laptop, and so this is word count with group by key, shuffled read of 48 kilobytes, and doing the same thing with reduce by key resulted in 1/4 the amount. So it resulted in a shuffled read of 11 kilobytes, and that's because it's able to perform the reduction earlier. So we get essentially a free map side reduction before we do the shuffle. So even our shuffle is less expensive when we use the right tools. So essentially, we want to use reduce by key or aggregate by key rather than group by key almost every time. And then we can be happy like this cat stuck inside of a loaf of bread. So we can also get problems with just the shuffle, right? Just shuffling our data can cause problems. So if we call sort by key on our handlebar mustache example, we can end up with having a partition which is too big. There's still this 2 gig partition problem. And even if it did succeed, we would end up with sort of unbalanced partitions. And so this looks very much like instead of our handlebar mustaches all just going over to the right, they've now just all gone down here too long. And if we were to perform some type of later function and this hadn't failed, we would have 2 very fast partitions and 1 very slow partition, and that would be quite a waste. The solution is we can just add some junk to the end of our key, right? And then Spark's actually able to split it using this junk bit, and we can end up with a nice distribution because sort by key actually samples our data to come up with where the splits should be. We get this really nice distribution. And actually, this is a kind of interesting side note. There's a tiny bit of magic inside of the shuffle. Well, actually, there's quite a bit of magic, but the part that I care about is shuffle files. So when we shuffle, Spark actually writes these files out. And frequently, these files don't actually hit disk. They end up just in the OS page cache. But we can actually reuse these shuffle files. They're not automatically deleted. And so if you have a shuffle, and then you are going to do multiple things with that RDD after the shuffle, you don't necessarily need to cache that RDD. The only little downside is that sometimes this can and does explode. And that's because shuffle files aren't really garbage collected. And that's fun. Your RDDs are garbage collected, and once the RDD itself is garbage collected, the shuffle files it's associated with will get deleted. But if you have a huge amount of memory on your driver program, so that you're not getting GC events on your driver program, which is like a very reasonable decision, you could end up in the case where you end up having these shuffle files starting to fill up on your worker. And in that case, you can work around it by manually triggering a GC event. Doing that from Python, kind of crazy. We'll look at how to do that next. Well, not exactly. We're going to do data frames, and then we'll talk about how to do this next. So data frames are our savior from a lot of the performance problems of Python. They get around this double serialization and passing the data from the JVM to the Python worker. The notable exception is when we try and start extending data frames with UDFs. So once we start adding a UDF, it ends up copying all of the data into Python anyways. But for the places where we're able to use SQL expressions, it actually takes those SQL expressions and it's able to evaluate them inside of the JVM. That being said, for people coming from Python and you're hearing Spark DataFrames, you might start to get really, really excited. But as it says in red, Spark DataFrames are not Pandas DataFrames. And if you're coming from R, they're not R DataFrames either. And you should really lower your expectations down to just about here. Yeah, okay. Sorry about the feedback. I should have thought that through. But anyways, so they're really powerful, but they're definitely the kinds of things which are easy to implement in a distributed system, right? And Pandas has such a huge array of functionality, not all of that stuff can be implemented in Spark DataFrames quickly. But on the good side, right, we get really amazing performance with them, right? So provided that we understand the limitations, it's really, really quite a wonderful system to work in. So instead of providing Lambda expressions like we do with RDDs, we provide SQL expressions. And so we say like df column equals true instead of lambda x dot happy equals true. So when can Spark SQL benefit performance? Probably this is very much preaching to the choir, but if you have structured or semi-structured data and you're okay with not having absolutely everything under the sun available to you in terms of types, if you were the kind of person that had like a weird custom Python object you were sending over the wire inside of your RDDs, you're not going to be able to do that with data frames. But if you like had a whole bunch of like really complex nested structures like dicks of dicks of dicks with like hashes and like crazy stuff, you're good. You're good. Yeah, right. If we only need to operate on a subset of our data inside of certain operations, it's really fast because we've got this columnar-oriented store. And we get this, our cat who was wearing the magical hat in the first slide gets some magic powers. And we'll look at those magic powers. But the most important thing, like the Catalyst optimizer is great, but even if the Catalyst optimizer wasn't great, being saved from this double serialization cost is a huge thing, right? Yeah, and we already talked about this. The really big thing from my point of view, from the point of view of the optimizer, is that it's able to look inside of our operations, right? It's able to tell the difference of us trying to compute the minimum of something and us trying to compute a list of something, right? And if we're trying to compute the minimum of something, it can do a lot of really intelligent optimizations. And if we're trying to compute the list, I mean, we were probably pretty much screwed at the start anyways, but it'll do the best it can, and we'll actually still get some speed up. So in Scala, it can be a lot faster. Red is group by key, which at this point we all know not to do. And blue is reduce by key, which is actually like the right way to do it. And we can see that actually Spark SQL outperforms the right way, even in future iterations when the JIT has had a chance to warm up. And part of that is because it's got a more efficient representation of our data, and its serializers are much faster. And in Python, the difference is even more astounding, right? The red line continues to be a very bad red line, but the blue line doesn't actually get us that much faster, right? And that's because we still have to pay this double serialization cost. But in Python DataFrames, it doesn't matter, right? We're not paying that double serialization cost. We have a tiny amount of overhead to call the JVM on the driver, but compared to copying our entire data, it's nothing. It's great. So word count with data frames, right? This is a natural extension. And this is actually surprisingly faster than word count with RDDs in Python, even though we are using this lambda expression here. And for this one part, we will have the double serialization cost. But for the other parts, we won't have the double serialization cost. And that's because we're essentially, here I'm using a flat map, but normally you would probably use like a UDF. And I'll talk about some plans to make that not so bad soon. So we could make a UDF to do the same thing. But even if we made a UDF, we would have a double serialization cost. Yeah. The cool thing, though, is we could call Scala UDFs really easily, or somewhat easily. We can call Spark Scala UDFs really easily. And if we have our own UDFs that we've written and we're willing to port to Scala, we can call them using Py4j and a fair bit of magic. So what does this look like? We can define our little Scala function here. Evil SQL tools is not part of the Spark package. I know you are all shocked, but in this case, evil SQL tools is just a convenience function to get the expression. You don't actually need to use it, but we can write our Scala function, whatever it needs to be, and then we can start actually passing things to it. So the Spark context has a Py4j gateway on it, so sc._gateway. And we can also actually access a whole bunch of other things inside of the driver program. RDDs are wrapping Java RDDs. They're not very useful for this purpose because they contain pickled objects that Java can't really understand anyways. But if we happen to be working with data frames, the df._JDF is actually very usable on the Scala side because it's just a regular Scala data frame. And it can go ahead and use that. And we can actually take our Python data frames and pass them to Scala, do some really weird, expensive computation, and then bring them back to Python for the rest of the work that we want to do. And so here's how we can register some SQL extensions. So in this case, this is from the Sparkling Pandas project, which is long since gone. Or, well, maybe not super long since gone, but is gone. But essentially, com.sparkling pandas is clearly not a part of Spark, right? Well, it does have the Spark prefix, not a blessed package. So if you have your own Java code, you can add it as a jar in your Spark submit, and then you can just go ahead and reference it this way. You can do ._JVM, and then just give it the full path, and you can actually just go ahead and call your function there. And now we've registered some UDFs that we can access from the Python land. It's kind of cool. Actually, now that I think about it, there's a better example of this in the high-performance Spark examples GitHub, if anyone happens to be interested in doing this, or at least there should be. There are some downsides to using data frames in Python. One of them is that the schema information right now from Spark gets serialized as JSON and shoved back to the driver and back and forth and back and forth and back and forth. And like that's okay for really small schemas, but if you end up having like 200,000 rows in your schema, maybe you are reading from a NoSQL database like the people before me, you might run into some performance downsides, and this can be slightly problematic. It's important to remember that 2pandas is essentially collect. And I'm going to skip ahead because I want to talk about some fun things. The future! Okay, so I think, and I'm really biased, but I think the future is awesome UDFs. And I think there's a few different ways we can get there. One of them is if we bring the dataset API to Python properly and we expose map, we can actually do some of the crazy things that they're looking at doing in Scala in Python and try and convert simple Lambda expressions into SQL expressions. For people who have really simple UDFs and don't mind running in Python 2.7, we could try evaluating some of your UDFs inside of Jython. And actually, I'm going to go ahead and grab this. Ooh, come over here, pull request. And I'm going to make that, oh, damn it, stupid presentation software. There we go. I'm going to go ahead and make that pull request right now. It's a very early stage pull request, but if anyone's interested in seeing Python UDF evaluation inside of the JVM for simple UDFs, I've got a work in progress pull request now for that, and we'll continue from here. And yeah, so in my really early benchmarking, it seemed to be about within 5% performance of a native Scala UDF for some very simple code, and about 65% faster than regular Python. If anyone has simple Python UDFs that you're willing to share with me for benchmarking, I have a little survey here. It's bit.ly/PySpark UDF. And I would really love your UDFs so that I can actually benchmark it on other people's code and make sure that you'll get performance improvements and I'm not just being crazy. Yeah, here's a graph of happiness. The red is Python, I think. Yeah, the red is Python, as is the blue, and the orange is Jython. And you could intermix the two, right? You can write most of your Spark program in regular Python, and for the really simple parts, you can have them evaluated with Jython, and you'll get this like nice performance improvement. The other thing that's really exciting for people that saw Wes's talk is fast interchange, and hopefully, I think it'll be really awesome. There's both on making two pandas faster, and that involves making Arrow something that we can serialize data frames to, and then there's also the possibility of using something like Arrow for on the worker side for UDF evaluation, so that we can actually just like copy the data faster than moving pickled bytes around. Yeah, and if anyone cares about testing, I've got a bunch of shit on that. There's some really cool Python libraries. I'm co-author of one, and then there's another one for people who like PyTest. And some other general Spark resources. For you all, you probably already know all these resources, so we'll skim over that. There's a bunch of Spark books, and I'm going to tell you not to buy one of my books, even though it gets me the most money of any of the books that I've written. Do not buy the first edition of Fast Data Processing with Spark. It is pretty bad at this point. It's really out of date. I recommend many of the other books, even the ones where I don't get money from them. And so when an author is recommending a book where she receives no royalties over one of her earlier books, that's a pretty good sign. So I think Learning Spark or Advanced Analytics with Spark are both great. I'm running out of time, so I'm going to try and get you all to give me money. With High Performance Spark, you can buy it from O'Reilly. And you can also give me your email address to spam, contact selectively once the book is available for purchase. And I am just out of time, so I want to say this is Bun Bun, and she's really cute, and she's on a computer. And if you have questions, come chat to me after. I'll disappear outside.
Thank you. Big hand.